Hello, everyone. Thank you for joining our Concept to Completion webinar. We're going to wait just approximately a minute or two for some people to log in, and then we'll get going. Thanks for joining us. All right, let's get this thing kicked off. Like I said, thank you for joining us for our Concept to Completion webinar. We are going to be focusing this one on aerial LiDAR and photogrammetric workflows, mainly airborne LiDAR, as that's kind of the hot topic now. So that's kind of what the journey that we'll be going on today. So for those of you that have followed our Concept to Completion webinar, we did our introduction. 2 months ago, we did our mobile mapping webinar, which is vehicle mounted LiDAR. Just about a month ago, we did our terrestrial scanning with Troy Hernandez, which was a really good one. And then today, we're going to be doing the aerial and drone-based LiDAR. We have myself and Bob Green here as moderators. We have Dylan monitoring the chat. So as we go through this webinar, if you do have questions, please drop them in the chat box. Dylan will be monitoring that. And if there's a few things that keep coming up, we'll come through at the end. We'll answer some questions and we can have a conversation there as well. In about a month from now, we'll have our construction or build related scanning webinar hosted by Robert Beck out of Building Point. And then Bob, do you want to come in and introduce our final webinar?
Yeah, originally we were just going to have the final one be the build webinar, and I was going to put the actual final deliverable on a plat and with metadata and everything at the end of this one. But once I started looking at it, it's just too involved. So we're going to do a final one where we're going to present how we put all this 3D data together, coupled with the survey analysis and more statistical related, so you can kind of see the deliverable plus how we created it, and that'll be in probably the first part of December.
All right, thank you, Bob. That leads into a good transition here to introduce Bob Green, a professional land surveyor. He's been working at Frontier Precision now for just over 3 years, but has a lot of knowledge and depth of experience lasting 45 years. One awesome thing about having Bob on staff here and working directly with him is he's seen this technology in its infancy and watched it grow into kind of what we'll be talking about today. And then we have myself, Nathan Stevenson. I've been working at Frontier now for 5 years as an applied geospatial engineer. I have a couple of degrees. Mainly what I focus on here is mobile LiDARs. That could be vehicle mounted like we went through 2 webinars ago, or more recently airborne LiDAR. Like I said, that's the hot topic now. A lot of people want to talk about it. A lot of people are jumping into aerial LiDAR. So that's why we're having a aerial LiDAR focused webinar today. All right, so the first thing, let's get this kicked off. What is aerial LiDAR? I'm a young guy, we like memes, so I'm gonna start this off with a meme. I like this meme here. Not only is it funny, but it's very pertinent. So on the top, we have Captain America holding his shield. We have photogrammetry not being able to penetrate this proverbial shield, which is tree canopy or vegetation. So in the past, even now, traditionally speaking, photogrammetry is a passive remote sensing technology. It doesn't actually touch the ground. It doesn't actually measure anything. It just takes passive photographs, right? So in tree canopy, or even with large bushes, things of this nature, it really struggles to get to the true ground. On the lower part of this meme, we have LiDAR breaking through that shield and getting to the ground. So this here is a picture of photogrammetry data, right? So this is a passive remote sensing technology once again. If you see, we have a bunch of points up in the sky. These are some really thick evergreen trees. And below those trees, we have no data. So just like the meme shows, heavy tree canopy, photogrammetry just simply cannot go through that vegetation. It's a limitation of the technology as a whole. But that's not to say it's not useful, right? We have awesome data on the ground. If flown with the proper heights and overlaps, you can do really good curb and gutter as well. And then we have this beautifully colorized point cloud. So let's not discount photogrammetry, it just struggles with vegetation. And then we have the man of the hour, LiDAR. So this is a image, it's really a cross section of some LiDAR data that we collected up in the Pacific Northwest, specifically Seattle. For those of you that are familiar with Seattle, it's very dense vegetation, very tall trees, evergreens, things like this. This was using a yellow scan Voyager. And as you can see with this cross section, we cut right through those trees down to that ground. And we get plenty of data that we can model this into a surface. So going off this concept of what is aerial LiDAR, one of the questions that we get a lot is, can you colorize aerial LiDAR data? If we go back to that prior image of photogrammetry, it is by nature colorized because we're taking pictures. LiDAR data is not, however. So we get this question all the time, can you colorize point clouds derived from airborne LiDAR? And the answer is yes. So in this upper left-hand corner, we have some colorized data. It might be difficult to see, but you can even see some white cars and red cars that are properly colorized. We can do so because we integrate cameras with each of these LiDAR sensors that are co-bore sighted together. So you're simultaneously collecting this LiDAR data as well as imagery, and then we can drape that onto each other. So in the lower left-hand side here, this is the drone that was flown to collect this point cloud. This is a DJI M300 and a yellow scan mapper, one of the flagships that we've been selling over the past few years. In the upper right-hand corner, this is another cross-section similar to the last one. We had a customer approach us that said, hey, we have an interesting job here. We're trying to collect contours of this pretty big slope, 45 degrees, 40 degrees, something like that. And their equipment was really struggling. Not only was the equipment struggling because there was very dense vegetation, but physically speaking, they were struggling because the slope is so huge. It's at such a steep angle. So they said, hey, can you come out and do a demonstration for us and fly some airborne LiDAR? So we flew the same drone in the lower left, captured this awesome profile in a single flight. It was something around, I believe, 80 acres, and we captured it in about 15 minutes. So this is kind of what aerial LiDAR is. For those of you that have followed us through this webinar series, this is the exact same slide that we used in our introduction. So I don't want to spend too much time on it, although for new attendees, I do want to just reiterate some of the airborne applications for aerial LiDAR. So Frontier Precision, our bread and butter is serving land surveyors. So it's no doubt that one of the things that we see the most is raw land development surveys. So think of an area that has trees and vegetation and brush, raw land, and there's going to be a new road or a new community or building some houses, something like this. And we need to survey in that land for hydrology, for contours, for a surface, all of those things that you need to do as a professional land surveyor. That's one of the things that we see this technology being used the most on. Another interesting thing that we see a lot is power line surveys. So traditionally speaking, power lines are built. There's vegetation around those power lines that are trimmed back. And at some time in the future, that vegetation needs to be trimmed again. So most of the power line companies, they hire helicopter crews to fly these lines with a helicopter. And it's sort of a biased approach, like, is this vegetation close? Is it really close? We can't actually put a value to that, like 10 feet from the line. It's sort of this biased measurement where you're just looking at it with your eyes. So one of the big things that we see is flying these power lines with LiDAR. We can actually assign values. We can say this tree is 5 feet from this line, this tree is 10 feet from this line, and we can actually assign those values in an unbiased way. One of the other things that's not really an application, just a general thing for aerial LiDAR, is the efficiency and ease when it relates to surveying, engineering, and mining. One of the big things that we see is the reduction in ground control. So going back to my very first couple slides, photogrammetry is a passive remote sensing technology. So it needs a hefty amount of ground control to maintain accuracy. Since LiDAR is a active remote sensing technology, we can reduce that ground control and still maintain accuracy. We'll talk about that a little bit at the end when we bring Bob as a land surveyor back on. One of the other big things too is with photogrammetry, we're really limited by sun conditions, right? In the perfect world, we'd be flying at solar noon. That almost never happens. Sometimes we fly early in the morning or late at night and our images are dark or overexposed, and that really can affect the data. So LiDAR, one of the big things is we eliminate that reliance on sun conditions. The data is the exact same, whether it's in the nighttime or in the day, in the afternoon, it doesn't really matter. The technology works the same no matter what. All right, so let's jump into some data from our project. So in this concept of completion webinar, one of the things that we wanted to do is not just rely on canned data or canned slides from manufacturers. We wanted to go out, collect our own data, and show us processing that data into a final deliverable. So that's what we're gonna do. We used a DJI M300 with a yellow scan mapper, that same drone and LiDAR combination that I showed in a previous slide. All right, so let's jump into what the data processing looks like. So I kind of wanted to go start to finish in images, showing the data processing. I think even a lot of people nowadays, they get turned off by LiDAR thinking that it's a very complex thing. You need somebody with a math degree or a lot of experience to process this data, and that's really just not true anymore. So I wanted to show start to finish what data processing looks like. So there's a lot of different manufacturers out there. The one that I'm kind of highlighting here uses a software, step one software called PausePack. This is made by a company called Applanix, who is owned by Trimble. So for those of you that are Trimble Business Center users out there, this looks awfully familiar. It looks exactly like the interface of Trimble Business Center. So once again, this is called PausePack. So basically, there's only a couple of steps in this software. We're going to input our trajectory file, which is this back and forth purple line here. Think of this as exactly what the drone flew in the sky. That's called your trajectory. And at start, just like any data, this is a raw trajectory. So then we can import our base data. In this case, we used an on-site base where we set up an R10. It's called 6042 right there. You're not limited to just on-site bases. You can also use a core station. And this is something we can talk about offline if anybody's really interested, but we can also nowadays use satellite-based corrections. So we go baseless, right? There's no base on site. We're not using a core station. We can use satellite-based corrections. All right, so the first step in this process is we're going to submit our base data to Opus. If that's your workflow, if it's a core station, we don't necessarily need to do that. But those of you who are familiar with RTK survey, we'll go out there, we'll log a static on our base, we'll submit that to Opus, and we'll use that to adjust all of our survey shots. The concept is very similar here. We're going to update our base location using our Opus corrected solution. And then we're going to run a fancy tool that basically updates the drone's location as well. Very, very similar to RTK. That tool is called the GNSS inertial processor. And if you break that down, we have two components there, the GNSS component and the inertial component. And we're taking those two things and marrying them together. This is an automated tool. All you do is click run, and it produces this data for you. So what I have up here is this is a relative accuracy graph. So not absolute accuracy. It's not like we go out and we check this stuff. We'll show that later on. This is relative to itself. So this is very typical. This is what we would expect to see. And I wanted to point something out here that I find interesting. We have these little increased inaccuracies, or I call them little wiggles and jiggles in our relative accuracy. These are actually turns. So when the drone banks, if you think about it, the GPS antenna that's on board loses a bunch of satellites and has to reacquire them. When that's happening, it loses a slight amount of accuracy. When we get into the next software, we actually clip this data out. Even though it's only a little bit less accurate by a couple of millimeters, we want to put our best foot forward and keep the best data. So we actually clip this stuff out. So I'll show that here in a second. Okay, so we processed our trajectory data using a on-site base, but what actually is this? What behind the scenes, what is this data? So I opened up the export from this PausePack software inside Notepad or Word, just some kind of Word reader. So we got our header here, which shows a little bit about when this thing was started and its origin and all this stuff. But if we look, if we break this down into its nuts and bolts, what this system is it's a GPS logging at 1 second static, very similar to what we would do using a base in the field. And then we have an inertial sensor that logs at 100 times per second. So basically we have this massive graph, 100 data points per second for the duration of the flight, however long that may be, 10 minutes, 20 minutes, and so on. So if we break this down, we have a time component in the lower left here, and then we have a massive graph of information that goes from latitude and longitude and ellipsoidal heights and degrees. We have some orientation angles, and then a lot of other information, velocity, roll, pitch, yaw, in this massive, massive table. So that's what this data is behind the scenes, right? So if I jump over into this next software here, this is called YellowScan Cloud Station. Most LiDAR manufacturers have their own proprietary software that they produce, because most of these scanners come in proprietary file formats. So we're showcasing YellowScan here. There are different options out there. But basically what this software does, it's very easy to use. There's only a couple of buttons. It reads in that massive graph that I was just showing in the previous slide from PausePack. It applies those updated values to our trajectory and then uses that to compute a point cloud, which is what we're seeing on the screen. So this point cloud right now, it's just colorized in an elevation view. So the darker greens are higher than the lighter greens. This is a fairly flat area, so there's not a whole lot of elevation relief to show. So let's jump into this software a little bit and just show you some of the power and some of the data that you get out of it. And I think you'll be really interested to see. Okay, so one of the things that we can do in this software is cut cross sections. So in the upper level here, we have an intensity-based view, which I'll jump into in a second. You can see a little red cross section that I'm cutting, and then on the bottom, we're viewing that cross section. So this shows a number of things. One of the biggest things that we can see is even in these big tall trees that are all clumped together, we're getting lots and lots of data under the ground. The other thing that we can see right now, I have this colorized in what's called a strip view or flight line view. So basically each flight line that the drone flew is a different color. And in aerial LiDAR, this is one of the most important things to look at, how well aligned your flight lines are. And that goes all the way back to the manufacturer and how well they calibrate their systems. So one of the great things about YellowScan is their systems come factory calibrated, and they're calibrated very, very well. So basically what we're looking at here is the different flight lines. Let's say we went north for a flight, and then we came back south for a flight. There's some overlap between those two things. What we want to see is that these colors that are colorized by flight line are on top of one another, or the sides of buildings match. There's not duplicates of things. So that's kind of what we're seeing here. And it's just a really important thing in aerial LiDAR. So this is just an intensity view. For those of you that are unfamiliar with intensity, a beam of light comes out of these laser scanners at 100% intensity. It hits something like the ground or a paint stripe or a tree. It comes back to the sensor, but not at 100% intensity. So we're colorizing this by the percent intensity that returned to the scanner. So what you'll notice right away is we see things like road striping, turn signals, the transition from grass to concrete. We can see all these things. That's just a native thing inside laser scanners. So we don't always need to colorize this data. For example, we don't necessarily need to see that grasses are green, the sidewalk is tan, or whatever color it may be. We can see some of that stuff in this native intensity view, which is something that I think is an underutilized thing in airborne LiDAR or in scanning in general. Okay, so there's a few more things that this software does. One of the things that I was talking about is how well your flight lines line up. So that's really important. There's some reasons why your flight lines wouldn't line up. Like for example, let's say we're using a core station that's a good distance away, 10, 20 miles away, and our overall solution status isn't great. That can lead to some misalignment within our flight lines. So YellowScan and other manufacturers, they have fancy tools to work out some of that misalignment and bring those point clouds back together. In this software, it's called strip adjustment. It's a single button, you click it, and the magic happens behind the scenes. There's a couple of other modules. So this is very similar to Trimble Business Center, where you have your license to the software, and then you can add modules as needed. This software is very similar. So one of the other modules is the terrain module. So aside from making sure that your flight lines are lined up, the next most important thing is reducing this data into something useful. So we have trees and buildings and cars going by and signs and all this other stuff, but maybe all we need is true ground, right? So we can derive some contours, we can look at a bare earth surface. So we need some software that does that for us, that eliminates the trees, eliminates the fences, and gives us just ground. That's what this tab does. It's called the terrain tab or the terrain module. And we'll jump into that more in just a second because, like I said, it's one of the most important things in airborne LiDAR. Finally, they have a colorization module. So if you did have an integrated camera, this module would drape those photos over your LiDAR data, and grasses would be green, asphalt would be black, that sort of thing. Okay, let's jump into that terrain module that I was talking about just for a second. Like I said, it's a very important thing getting to true ground. So one thing that's awesome about this, it's not just a black box where you click a button. You can adjust some of the parameters as it suits your site. So they have some preset ones like flat, hilly, steep, extreme, maybe in your mountainous terrain. For this, I just selected flat. So they have these preset terrain types, but then you can also tweak those a little more. We can go in between flat and hilly by adjusting that steepness value that's set to 0.01 right now. And you can run this in an iterative fashion. You can say, I don't really like those results. Let's run it with a different steepness value. You can do the same thing with minimum object heights. So if there's lots of trees or little bushes or things like that, we can tweak that parameter to help eliminate those things so they don't mess up our contours later on. Finally, we can also adjust our point cloud thickness, which is important if you're using less precise scanners. We want that to be kind of thick. If you're using more precise scanners, we want that to be kind of thin. So what we're seeing here are the results. Everything that's orange, the software believes is not ground, and anything that's gray, the software believes is ground. So once again, I'm cutting a cross section here, and I'm displaying that results on the bottom here. And you can see it does quite well. We have some trees, we have some houses, we have some even small features like little fences in between those houses on the left-hand side. And you can see that the software is categorizing those correctly as not ground. And it's categorizing ground correctly as well. So then basically it segments those into classes. One class is ground, one class is not ground. And that'll come into play later when we derive surfaces and other deliverables as well. So lastly, you just export the data from the software. You do have to export into a known coordinate system, such as a UTM zone or a state plane, something like that. Right now, it does not support non-published coordinate systems, like for example, 10,000, 10,000 site, or maybe a truncated state plane. It does not support that right now, but if you need to do that, if that's your workflow, get with myself or with Dylan after. Obviously, we can take this stuff from a known system into a custom system or a local site. We can do that inside Trimble Business Center fairly easily. So basically, I'm exporting this data out of this software. It has now been corrected using our base that we showed in POSPAC. And it also has these classes of not ground and ground, and we've placed it inside a coordinate system. For this specific project, we're in Colorado, so it's going to be in a Colorado state plane system. Okay, so I have this exact same data that we were looking at before. This is in an elevation view again, and I have a map behind it. We're now inside Trimble Business Center. This isn't your only option. When you're done processing aerial LiDAR data and we have a georeferenced point cloud, there's lots of ways you can go. We're a Trimble shop and Trimble Business Center is very powerful, so this would be one of the best tools, but there are other options. This is the one that we're going to show today. So I have a background map. Makes you feel all warm and fuzzy that we're in the right part of the world when the road lines up with the background map. You can see we're in US survey feet and we're in Colorado Central 0502 for this data here. Okay, so now we're looking at this in an intensity view, and you'll notice there's some data on the road as well. So 2 webinars ago, my colleague Dylan Jones, who's monitoring the chats right now, he went over vehicle mounted LiDAR, where we strap a LiDAR sensor to a vehicle and we drive by and collect this data, as opposed to airborne LiDAR, which is what we're doing now. And he extracted a bunch of informations, lane lines, curb and gutter, power poles, power lines, all this good stuff. So that's what we see here, kind of in the middle of this image, are all CAD lines or poly lines that was extracted from vehicle mounted LiDAR. And we have that draped on top of our aerial LiDAR right now. All right, so we extracted ground and not ground in that prior software. You can do so here in Trimble Business Center as well. And this is just a quick clip. I did a 1 foot interval. So basically sampled this into a 1 foot grid of data using our aerial LiDAR data. And remember, most aerial LiDAR isn't nearly as precise as vehicle mounted LiDAR. So you can see some little bumps in there. And that's pretty standard. That's what we expect with most airborne LiDAR. But what I want to focus in on is the curve on the left-hand side. So when we sample back this data to 1 foot intervals, maybe we have a nice curve profile, maybe we don't. It depends where the software samples it back. So you can see this curb is kind of jaggedy. There's not a great profile. You know, maybe you wouldn't want to use this for engineering purposes or road redesign purposes, but we have this curb, right? So we have this data, and we've been talking about this whole concept to completion webinar using multiple sensors and doing what I like to call is sensor fusion, taking the best from one sensor and the best from another and putting them together and getting the best of both worlds. So what I've done is I've taken the CAD lines, the curb and gutter profile that was extracted by my colleague using a vehicle mounted scanner, and used those as brake lines for our airborne LiDAR. So if I update our surface doing that, all of a sudden now you see we have this near perfect curb profile derived from brake lines that we got from our vehicle mounted sensor, but then the overall surface is from our airborne LiDAR. So one question that we get all the time is, how do these two things stack up, right? Like I mentioned, vehicle mounted LiDAR is much more precise, much more accurate. There's a lot of reasons for that. They're high-end IMUs, higher grade GPS on board, and more so than that, they're only a few feet from the ground, right? They're on top of our vehicles. Airborne LiDAR is a few hundred feet from the ground, 200 or 300 feet from the ground. So it's obviously a little bit less precise, but let's just look at it. So using the brake lines from the vehicle mounted scanner, obviously our curb profile is going to be nearly identical. So what we're looking at here, the blue surface is from our vehicle mounted LiDAR and the green surface is from our airborne LiDAR. Since we use the brake lines for both, the curb profile should be nearly identical, which is what we see. And then you can see that nice, smooth vehicle mounted surface derived from a vehicle mounted point cloud. And then you see it's slightly less precise, but remarkably similar, considering we're flying at, in this project, 250 feet in the air. So what we're going to do at the very end when we do our final deliverable that Bob was mentioning is we're going to take the best of all these worlds. We're going to use our vehicle mounted LiDAR to get that precision on the road and on the curbs and on things like power poles. And then we're going to use our airborne LiDAR to get really good data underneath trees and there's a river that's running through this, getting edge of water and stuff like that. And then as we get into the terrestrial stuff, we'll show some stuff at the end here that shows where that'll shine as well. So here's just another image. This is also from our airborne LiDAR. So this is a river, like I said, a kind of drainage running through here. It's not man-made, but it has been man-modified where they have some retaining walls and stuff like that. But basically we're looking at the sinuosity of the river here, as well as the surface beyond it. So this is after we've extracted the ground and sort of eliminated the trees. So this would be what we consider a bare earth surface. And I just want to show what that looked like prior to that. So this is that same exact region here. We have obviously a bunch of trees, really tall trees. There's some underbrush. There's a bunch of reeds and stuff like that growing next to the river profile there. And this is, if I go back, right, eliminating this stuff and getting really, really good ground data that we can even ground truth using GPS or total stations really is the power of these types of systems, right? Getting data in almost inaccessible, or I should say areas that wouldn't be very fun to collect data using a total station. So one of the other questions that we get all the time is, okay, we have this awesome point cloud. It doesn't matter where it came from, terrestrial or airborne or vehicle mounted. We have this awesome, pretty picture. And Bob says this all the time. It really is just a pretty picture unless we can get the information that we need out of it. So maybe we don't need all this stuff. Maybe we just need edge of water. Maybe we just need this fence line, right? We need to be able to break this stuff down into kind of the traditional survey deliverables that you would if you broke out your GPS or total station, right? So I wanted to show exactly what that looks like to take some of these point clouds, no matter the sensor it came from, and extract some information out of it. So let's see if I can play the video here. Here we go. Okay, so we're simulating, this is a walking path or a bike path that goes through the middle of our study area here. How to extract that data. So I'm inside the CAD tab. I'm inside the line string tool. And I'm basically gonna just make this its own layer. I'm calling it bike for a bike path. And If you had a feature code library, like you have your own special feature codes, FH equals fire hydrant, whatever it may be, you can code that directly into these CAD lines or single CAD points, and that would follow over into CAD as well if you do use feature codes. For this, I just made one up and I called it bike path. Okay, so I'm going to start extracting this bike path here. Right there, what I was doing is I was changing my segment type from straight to smooth curve. And that's really important. Obviously, we're looking at a curved bike path here or a curved road. It doesn't matter which. You don't want to sit there and click a million times to get that curve. So what we can do is if we change our segment type to smooth curve, it'll interpolate that curve as we click just a few points. And then obviously we can change back to straight as well. So I extracted the left side there. I'm just going to extract the right side real quick, change my segment type to smooth curve once again. So it is as simple as this. Being able to see things inside of our point cloud and clicking on them, whether it be a polyline or it could be a single feature, right? Like the middle of a manhole, the base of a tree, whatever we may need. Whatever we can see and we can click on are things that we can extract quite easily like this. So in just a second here, I'm going to turn the point cloud off so we can look at just those CAD lines that I extracted here. One thing to note, there we go, there's our 3D polylines. So these do have X, Y, and Z coordinates associated with them. And we can use them as break lines in our surface. We can export them to CAD if we need to. So this software supports all of the main industry standard file types, DXF, DWG, land XML for the surface, and lots of other file formats that we can't even get into here. So that's one of the questions that we get all the time is how do I extract this down into just what I need? And it is as simple as clicking on what you need, putting in a feature code if that's the way you do things, and then clicking along inside this point cloud. So I wanted to show this next picture here in just a second. So I extracted this entire sort of sinuous bike path here in orange. And then all of that data that my colleague Dylan extracted using the vehicle mounted scanners to the left in orange. And one thing that I'll note here is I never connected the two, right? So you see the road is not connected with the bike path, and I'll show that why in just a second. So it's maybe a half a mile or something like that in terms of linear distance, and I extracted this in approximately 5 minutes. So it's quite fast. So we've been harping this whole time about, LiDAR gets you through vegetation. It has that power to get data under trees. And I just wanted to show a visual that I thought was really powerful in showing that exact concept. So this bike path kind of curves in and out of these trees. It's really nice. It's not far from our office here in Arvada, Colorado. But it's under really heavy vegetation. So we actually had a couple different GPS receivers out here just to do some ground truthing. And we had an R8 that was actually struggling, right? It was struggling to gain that precision that we needed to test this data because of these trees, right? A large percentage of the sky is covered. We're under some vegetation, right? It wasn't going well. We did, however, break out R12 with ProPoint, and that did give us the precisions that we needed to check this data, and we'll show that at the end. But this is a pretty cool thing. If you had to do this without LiDAR, you'd have to set up a total station, right? You'd have to have your rod man kind of walking through this, and there'd be a lot of setups because it's a winding bike path. All right, so let's do one more video here. So like I said before, I didn't connect the bike path to the road, and there's a reason for that. So I'm going to start extracting this bike path one more time and show why that is. All right, so I'm going to change my segment type to smooth curve once again because this is a curving part of that bike path. And once I rotate this here, you'll see there's some trees. Obviously, we have data even under those trees. Change my segment type back to straight. And all of a sudden, this is one of the reasons that we chose this site because it was so variable. The bike path goes under the road, right? There's also some drainages in here, but this is basically, it's a water drainage as well as a bike path that they raised a little bit so you don't get wet. So this is a little teaser going into our next webinar series, terrestrial scanning, and our ultimate final webinar series doing the final deliverable. We actually traverse through here using a tripod-based laser scanner, right? So Our vehicle mounted scanner obviously didn't get it because we were on top of the road scanning. Our aerial LiDAR scanners didn't get it because it's under the road. So you could do this with a total station as well. We chose to use a tripod-based laser scanner to traverse through these tunnels and register all of this data together so it's nice and tight, all 3 data sets that we have, all 3 data sets registered to control, so we know we're confident in our accuracy here. And I'm continuing to extract that bike path or walking path here. So this is kind of right here, it's hard to see, but this is where it comes out the other side. And if we look down from the top, I now have a CAD polyline of one side of the bike path, and I can continue on going and extracting this data. So we're not obviously limited to lines. Like I said, we can extract single points as well, manholes, power poles, tree locations, things of that nature. There's a lot of automated extraction or semi-automated extraction, and then there's almost limitless possibilities when it comes to manual extraction. So there's some data from our site. I did want to jump into one more thing before we wrap this up and take some questions here. I wanted to jump into a return on investment study. So a lot of people, when they hear LiDAR, it doesn't matter if it's vehicle mounted or aerial or terrestrial, they hear LiDAR and they associate that with dollar signs, big money. And in some cases, that's true. It has come down a lot in cost. But if we eliminate that just for a second, whether it's a entry-level system or one of the highest end systems, you still need to know what your return on investment is. When are you going to start making money, and when is this thing going to be paid off? So we went down this road with a customer who was thinking about buying one of the higher end systems, but like I said, this applies to them all. They wanted to survey a site side by side with us. So we would come in with our aerial LiDAR equipment, survey one site, and they would come in traditional boots on the ground survey, GPS, and do the exact same site. And we would record things like time, data accuracy, how long it took to compile everything, and really look at, is this faster? Is it better? What does this grant us, this technology in our toolbox? So this is the site here, is in Texas. It was a 1,000 acre site that was going to be a future solar site. I believe it is already now. This is about 2.5 years ago, 3 years ago. And this is what it looked like. A lot of scrub brush. There's some fences that are hard to see. And in the back, kind of hard to see as well, there's some power poles and power lines. And then there's this terrible creeping ground cactus everywhere that was a challenge to move through. So this is the site, right? All right, so just to go over some of the field operations, obviously I showed the office side of processing before. The field operations are quite easy as well. You assemble the drone and the sensor, which takes maybe 1 to 5 minutes to take everything out of its case, plug in the batteries, attach a LiDAR sensor, and do some planning. One of the things that I mentioned a little bit before in processing is all of these systems require static base data, whether that be on-site or from a core station, or as we get into the future, satellite-based corrections. So we're going to set up a base for static collection here. One of the things to note is we don't have to have a special base just for this aerial LiDAR. You can continue your everyday work doing something in your survey style called RTK and logging. So you're doing your RTK work, right? You're roving around, collecting the points that you need. That base is also logging the data that you need for LiDAR. So you don't have to purchase more equipment. You don't need a specialized base. You can utilize the equipment that you have today as long as it collects static. So obviously we can turn on the LiDAR scanner. We do some final checks, some safety checks, and then you fly. So it's pretty easy on that side of the fence. And these are some of the data products that we get out. I was showing these before, we'll show them once again. So we can colorize this in an elevation view. So reds are higher than greens, which are higher than blues. One thing to note, you'll see that kind of data void, that black gap in there. All LiDAR scanners, aside from some new ones that are coming out today, cannot penetrate water. So if they hit water, that beam is absorbed and you get no data. So that's actually a pond kind of in the lower left of our data here that you see from all of these different pictures that we have up. That's a pond. That water absorbs the radiation coming off the scanners and you don't get any data. So we have this colorized in an elevation view. Like I said before, your flight line overlap and your flight line alignment is quite important. So I like to look at that in the field. And I should mention this, that you can you can look at all of these things in the field. You can check your data in the field. That's one of the biggest differences between aerial LiDAR and photogrammetry as well, aside from the vegetation penetration qualities. You can check this data in the field, right? Since the sensor itself is collecting that point cloud, it takes maybe 5 minutes to plug it into your laptop and take a look and make sure you got the data you need. Traditionally, photogrammetry, or taking pictures, which is the science of taking two-dimensional images and creating 3D data products, you need some hefty computers, you need some processing algorithms. That all takes time. So usually you don't check your data in the field. You just check that your images look nice, that they're crisp, they're focused properly. But other than that, you actually don't know what kind of 3D data, what kind of accuracy you're going to get, because you just simply don't have the time to check it. And then obviously we have our intensity view as well here. So this is what 1,000 acres of aerial LiDAR looks like. You can see I have this colorized by different flight lines. So every flight line is a different color, and there's lots and lots of flight lines, right? I think this took 12 or 13 flights to gather that 1,000 acres. So this is going to be the basis for all of our deliverables for this return on investment study that we did. Just some quick stats. It was roughly 160 points per square meter. So if you imagine, that's a lot of data, hundreds of millions, or in this case, there's a couple billion data points. But just note, don't be afraid of file sizes. That sounds like it's a massive file. I want to say the total 1,000 acres of a point cloud was around 35 gigabytes. The surface that we delivered was more like 500 megabytes, right? So it can be reduced down. One of the other things to note too is aerial LiDAR, or aerial data in general, contains lots of grade breaks, right? So we have, in this specific scenario here, there's some rocky outcrops, there's some rivers running through there, there's fences, there's all these things that would be challenging boots on the ground way. And then we have data even in these inaccessible areas. So like I said, there's this terrible ground cactus, massive. We're talking like 50 by 50 foot cacti on the ground that are about maybe a foot tall, totally impenetrable. I wouldn't want to walk through there, but we're getting data even through that as well. All right, so as we've shown, we have the ability to classify this data. So in the upper point cloud, it's just a point cloud. In the lower point cloud on the right, brown is ground and gray or white is not ground. So we have the ability to do that in the software. It's automated, and we can remove that to get down to true ground. Also, we can adjust this data to control if we need to. As I mentioned before, we can put this on a non-published local site. It's not that difficult to do. And then we're using this to create our deliverables. So this is what a 1,000 acre surface looks like. I have a 1 foot surface on the left-hand side. Like I said, there's all these different grade breaks. For being a fairly flat, when we think of Texas, a lot of it's flat. There's quite a lot of elevation relief in this, and you can see there's even a river running through there. And then on the right-hand side, we have 5 foot contours. Just note, these are not smooth. You can smooth them, so I realize they're jaggedy. We can smooth these contours. This is just for this thing as well. So one of the other things that I forgot to mention on that prior slide is, with a single pass, or lots of flights, I should say, but with a single collection, we gather all this information, right? For this specific return on investment, we're using the ground-only surface as our comparison, but we're not limited to that, right? We have the location of all of the power poles. We have the number of trees that are on site. We have, is there one fence line or is there 2 fence lines, right? We have all of that information with a single deployment, which is another big thing when we're comparing traditional versus airborne stuff. Another thing to note is we'll never get rid of traditional survey. We have to check this data. Bob will come on in a second to talk about that, but we have to check this data. We have to log static. We're always going to have to check into monuments. Single discrete points that we need to collect are still better suited for traditional survey, so keep that in mind. All right, let's get down to the nuts and bolts here. So they had 2 crews. Each crew had 2 people. One crew was a gator, kind of like the picture here, and they set their GPS to continuous topo, and they just drove around all day, back and forth in transects, collecting all the data they needed. Like I said, some of the areas were inaccessible, some had that cacti, some had a bunch of trees and stuff like that. So then their other crew was a boots on the ground GPS crew that would, hop fences, whatever, traverse through some cacti, and then boots on the ground, walk around to get their GPS measurements. So both of those crews to collect the 1,000 acres, it took them 10 working days, so 2 weeks. To fly airborne LiDAR of this 1,000 acres, it took us 2 days. One thing to note too is it rained for about half a day, so we couldn't fly. So in reality, it took about 1.5 days, but let's just round up and we'll call it 2. So then in the office, they had to compile a ton of different job files, all of their field data from these 2 crews, put it together, create a surface, code a bunch of stuff. That took 4 days. It took us approximately 2 days. It was like 2.25 days to take all of that raw LiDAR data, run it through POSPAC, run it through Cloud Station, just like I showed before, and produce that 1,000 acre surface. It took us 2 days. So when we're comparing time only, it took 14 working days, the traditional 2 crew boots on the ground way to collect this 1,000 acres, and it took us 4 days to collect and process using aerial LiDAR. So there's your biggest return on investment right there, a reduction in time, so we can do these jobs faster. So how does that relate to cost as well? So everybody pays their crews differently. Everybody has a different rate for their field crew in office. You can plug in your own numbers to that equation before. But basically, so they had 4 people on the ground for 10 days, as well as their mobilization cost, right? They had a gator, they had 2 trucks, GPS gear, all this stuff. They estimated that it cost about $42,000 in cost for them to collect this 1,000 acres. Since we're only there for 2 days, we don't need any gators, we don't need any of the special equipment, just our LiDAR scanners. We estimated it cost us about $15,000. Same thing in the next line item here, we see their office time, which theirs was 4 days, including the software used, and then ours was 2 days, including the software used. So I get this question a lot, why isn't our office time half the price? Well, a lot of these software, we're using Applanix POSPAC, Yellowscan Cloud Station, Trimble Business Center, right? We're throwing a lot of different software at this to really hone in on and get the data that we need. So the office side can be a little bit more expensive. So that's why it's not half. But if we take that and we total it up, it cost them $50,000 to do this job. Using aerial LiDAR, it cost us about $21,000 to do this job. So there's your next big return on investment. We can do things faster, but you can do things more cheaply also. So that's one thing to note here. On the right-hand side, I have, if we focus, there's a point number as well as to the surface and the surface elevation. But if you focus all the way on the right-hand side, we have delta elevation. So what this is, we basically have our aerial LiDAR surface, and this company went out and they checked it. They checked into a bunch of points, they checked into a bunch of targets, and what we're seeing here is the difference between their GPS shots and our aerial LiDAR shots. And Bob, if you're still on, do you want to jump in here and explain that a bit further?
Yeah, this report is pretty handy, points to surface report, irregardless of how you collect your data or what sensor you use. And here we're kind of averaging probably like 3.5 hundredths. It's kind of funny too that we're talking about this because last week, Nathan did a job or partnered with a customer. They currently don't have LiDAR and may not even purchase it in the future, but he gave us all of his panel point control, and Nathan worked with that control and constrained to it. And it's kind of funny because we're constraining, yet we get really good answers just from the product itself. And I'll go into that a little bit more in a minute. Come to find out, he had taken some check shots that he didn't share with us. And I talked to him yesterday, and everything checked out. So it's the surveyor did that without us even knowing it, and come to find out, all of his check shots work with Nathan's LiDAR surface. The other thing I'd like to mention also is these drones, we prefer PPK. And it's kind of funny because you don't hear about it too much anymore. Once RTK came out in the 90s, I mean, yeah, the middle to the late 90s, everybody knows that technology. But the issue is you're getting an instant in time, you're getting a position, one position. Whereas in kinematics, or while moving or in motion, we can process it forwards and backwards. So we have redundancy out in the field. So that's kind of cool too, that we're going back in time decades to when Dr. Ben Rumundi invented kinematic principles. So anyways, also on the POSPAC side, it utilizes the same coordinate system manager as TBC. So that makes it kind of handy for existing Trimble customers as well. I don't know if you noticed it when Nathan was on that particular slide, but it also has a RTX interface for post-processing. So there's lots of benefits to it as well. And that RTX technology keeps moving forward. I actually had an article in American Surveyor magazine last year. If you go to their website, it's got Bowman on the cover. Then a follow-up article in a Colorado publication, Side Shots. And then we just made the cover of American Surveyor this month with my Hoover Dam survey. We surveyed from the Mexican border up to the Hoover Dam, 342 miles with static analysis. And we also checked in with RTX. So that's pretty interesting. And I'll be presenting that at Trimble Dimensions. With these units, you're paying for IMU and echoes or returns. It's basically that. The fewest we have is 2, and then we can go all the way up to, I believe, 15 returns with our Voyager. Also, in this particular project, Nathan showed you an Opus report. Typically, if anything might go to court, I typically don't rely upon the federal government for my answer. I do my own network adjusted least squares survey and analyze it, and then I use the government to check my own work. And if you want to know more about that, I have plenty of training videos on our on-demand training website. Other thing I'm going to be doing is an experiment. As Nathan said, that these units, depending on unit, on type, are logging at much faster rates. So, 20 hertz, 100 hertz, whatever. They're logging at a great rate. So, say 20 hertz is 20 times per second. You log on your receiver, typically 1 second data. So software has to interpolate, and we use linear, quadratic, or cubic interpolation methodologies, whatever. But what happens if I take a lower end sensor and then beef up the integrity, because like in our R12s, you can log up to 20 hertz, and it's got plenty of memory, 6 gigabytes. So what happens if I log 20 hertz and only have to interpolate less data? So that's going to be an experiment that I'm going to do probably first of next year. On that Hoover Dam survey I did, we actually use what's called green LiDAR, which is for penetrating water. So we were able to get to the bottom of the Colorado River, and our survey was controlled for that green LiDAR. And it really came out quite amazingly well. We didn't do quite as long of sessions as I would have liked, but nonetheless, it all came out great. We used RTX as the backup. The issue in the industry is becoming perpetuation of where this data came from. That's another article I'm working on, of how do we perpetuate, especially if it goes to court. I mean, for day-to-day work, it's really not a big deal. But if it's, boundary line dispute or anything like that, recognition, acquiescence, adverse possession, or whatever, we definitely want integrity to our data. And the more less paper I see through the black, the better. So anyways, that's it for me. It looks like we have about 6 minutes left for questions.
All right, thank you, Bob. So as you alluded to, we'll spend the rest of this time, and we can even go beyond if we need to do some questions. Before we do that, my personal email is nathans@frontierprecision.com. One of the other ones that I don't have up here is if you want some information on drone related stuff or UAS related stuff, we have a dedicated email. It is UAS@frontierprecision.com, and that goes to about 15 or 16 people, and someone can help you out. So Dylan, do you want to go over some of the questions that you didn't get to answer, and then we can have a conversation about them?
Yeah, I answered most of the questions just via the question portal, but there's some that I think would be helpful to answer as a group here. And so one of those is, how does LiDAR get through to the ground? Is it line of sight, or can it penetrate leaves? Basically just asking, how does it penetrate through vegetation?
Sure, you want me to take this one, Dylan?
Yeah.
Sure. Okay, so LiDAR in general, Bob alluded to this as well. There's really two ways that LiDAR gets through, and I'm doing air quotes right now because it doesn't actually go through anything, but through trees and vegetation and down the ground. Way number one is just sheer volume of points. So if you think about a total station, right, most total stations take a single shot. Some scan nowadays too, but a single shot. This is similar in technology to a total station, although airborne laser scanners are usually taking hundreds of thousands of shots per second. So the one that we've been talking about here is the yellow scan mapper. It does 240,000 shots per second. So way number one to get through vegetation is just sheer volume of shots, trying to find its way through cracks in branches or little gaps in the leaves, things like that. The other way that Bob just mentioned is echoes or returns. So each of these shots have the ability to be broken from one shot into two. Like if it hits the very edge of a leaf, one beam goes back to the sensor and then it can keep on going. So it doesn't necessarily go through it, but finds its way on the edges and on the periphery. So some of the systems are single return, like most static tripod-based scanners are single return. Some airbornes are 2 returns or 3 returns, and like Bob said, we have a LiDAR scanner that's up to 15 returns. So the more returns you have, the better chance you have of getting to true ground. So hopefully that answers your question, Miles.
Yeah, perfect. Nathan, do you ever use RTK then on site for aerial LiDAR missions?
Yeah, excellent question. So 99% of LiDAR work that we do, at least I should say, is PPK, post-process kinematics. So we log static on the drone, we log static on the base, and in the office we put those two things together. There is an RTK LiDAR scanner on the market now. It's called the ZenMuse L1. You connect to your base, whether that be a DJI base or a core station. There's a lot of ways to do it. You can run that in RTK mode. That also happens to be the least accurate system. So one of the things that we have to think about, it's not as easy as we leveled up our rod, we're connected RTK, and we take a shot, right? This drone is going 20 miles an hour, wind is hitting it, it's wiggling around in the sky. All of those wiggles and jiggles, I call them, are logged onto the system, and we can work that out and smooth that out in the office. Had we done that RTK in the field, we would see some of that manifest in the data. So my opinion here is, and I believe Bob and other people would support this, is for this type of workflow, PPK is really the way to go.
Perfect. And then as far as that large project that you showed us at the end, did you use any ground control for that project? And if so, what did that look like?
Yes, we did. So, a lot of these systems you can operate without control and still have good data, but there's no way to prove that. So we always use control. We always verify our data and suggest that you do the same. So we put out special targets. They're similar to photogrammetry targets, just black and white ones, but they're a special material that can be seen in that intensity view. So if we're looking at this question screen here, you can see some road striping. So basically it's material similar to that we can lay out in the field and see it in the scan. And we use that to double check all this data, and if needed, to actually constrain to it. So one of the things that I said is a lot of these LiDAR manufacturers, you have to export the data into a known system, right? So for example, let's say we're in Colorado Central in State Plain, and then all of a sudden we're truncating that, we're lopping off a digit or two. Transforming that point cloud from a known system to a truncated system isn't always perfect. And that's where we'll actually use those ground control points to move around that point cloud so that they match as best as we can make them. You can do that in the software as well. So I guess to answer that question quickly is yes, we use ground control points. Yes, we constrain to them.
All right, maybe time for one more here. And someone was wondering, does Cloud Station have the ability to classify anything other than ground?
Okay, great question. So that software, YellowScan Cloud Station, can only do terrain classification, so basically ground and not ground, which by and large is what most people do. However, Trimble Business Center, the software that I was in showing surface generation and things like that, you can do ground, not ground. You can do high vegetation, power poles, power lines, trees, and you can actually extract metadata with that as well. So if you wanted to, like let's say we're using vehicle mounted data, you can extract the height of the tree, the diameter of the tree, the width of the canopy, things like this. So there's software that can automatically and semi-automatically extract lots of different information. Just depends what you're after.
Perfect. If we weren't able to get to your guys' question, we will definitely reach out privately and hope to answer those questions that you have, but that's all we have for the group.
Yeah, thanks you everyone for attending. We also have another one coming up. It's going to be our tripod-based build construction monitored by Rob, and that'll be coming up in about a month. So everyone should see an email blast coming out a week or so before that. Thank you for attending.